In this video here, we're going to take a look at volumes of revolution for parametric curves. Now, if we're given the equation of a parametric curve, we can still go on to find the volume of revolution for the given curve between 2 points by using the chain rule. Now, the volume of revolution forming the parametric curve with equations x equals f of t and y equals g of t is rotated through 2 pi radians about the x-axis between x equals a and x equals b. That is given by the following result here. So v, the volume here, that is equal to pi times by the integral then from a to b of y squared with respect to x here. So that's just our standard result here, right? Now, because we have parametric curves then, we can use the chain rule here. And as we can see then, this is equal here to pi times by the integral from t subscript a to t subscript b of y squared dx by dt dt. So in terms of the limits here then, just in case this confuses you, all these represent here is the value of t when x equals a and the value of t when x equals b. Okay, so we obtain these new limits here, right? And then similarly here, the volume of revolution formed when the parametric curve with these given equations here, so we have x equals f of t and y equals g of t, when these are rotated through 2 pi radians about the y-axis between y equals a and y equals b, this is given by the following result here. So again, v, the volume here, that is equal to pi times by the integral from a to b of x squared with respect to y here. So again, this is just our standard result here then, when we are rotating about the y-axis. And again here, just using the chain rule then, this is equal to pi times by the integral then from t subscript a to t subscript b of x squared dy by dt dt. So again, we have this slightly modified form here in terms of limits anyway. So we have t subscript a and t subscript b. So again, this is just the value of t when y equals a. Then for my upper limit here, this is the value of t when y equals b. Now, in a question, you can use either of these here for parametric curves. However, sometimes it might be easier to use the second part here. Obviously, it depends whether you're going about the x-axis or the y-axis. Or it might be easier to use the first result here. So it's completely up to you. Often, if a question involves, say, trigonometry, you're going to need to use this one here, right? So you need to use this one here if we have trigonometry, generally speaking, because it's not particularly easy to obtain the Cartesian form of the curve, right? So in that case, then we need to use this result here and obviously just use the chain rule. Same again here then, if we're about the y-axis. So that is something that comes with time and practice and experience with these types of questions. But we'll see a little bit more of that as we work through our practice question here. So there we have it. That gives us our introduction here to volumes of revolution for parametric curves. We don't need to go into too much detail here. I think that does cover pretty much everything. So let's get started then and take a look here at one example for volumes of revolution for parametric curves. So let's take a look then at this example here for volumes of revolution for parametric curves. So starting off then, what do we have for this question here? Well, straight away we have the curve C, which has the following parametric equations here. So x equal to ln t and y is equal to t squared minus 4 here. Now for the first part of this question then, nice and straightforward here, it just asks us to find a Cartesian equation for the curve C. So just basic A-level maths here for part A then. So for part A then, just finding a Cartesian equation for the curve C. How do we do that? Well, all I'm going to do here then is just rearrange this first equation here and make t the subject. And then we'll substitute that into the second equation here, right? So if x is equal to ln t, so x equals ln t here, we can rearrange this and make t the subject. So in that case then, t is equal here to e to the power of x, right? So in that case then, for y here, y is equal then to t squared. So if t is equal to e to the x, what we get then is e to the 2x minus 4. Okay, and there we have it. So like we said then, nice and straightforward there. That gives us the solution to part A. Now for the second part of this question, then what do we have here? Well, straight away we can see this diagram here, right? And the finite region R, shown shaded in the diagram above here, so we can see that here then, is bounded by the curve C, the x-axis, and the line x equals ln 4. The region R is rotated through 2 pi radians about the x-axis, and then for part B here, it says using calculus show that the exact volume of the solid generated is 4 pi times by 4 ln 2 plus 3. So what do we do then for part B here? So for part B then, well, clearly we're now looking at volumes of revolution here. So for V then, the volume, there's 2 ways to find this, right, when we have parametric equations like this. So the first way is to obtain a Cartesian equation of the curve C, and then we can just use the basic results that we know then already for volumes of revolution. If we can't do that, so let's say we have quite tricky parametric equations, right, that might involve, say, trigonometric functions. In that case then, what we need to do is use the chain rule. Now in this case here, this question is basically setting us up to use the first method then, right? Because we already have a Cartesian equation for the curve C here. So in that case then, V is equal to pi times by the integral here then. I'll come back to limits in a moment. And because we're going about the x-axis then, we integrate y squared here. So y squared with respect to x here. Okay. Now we know what y is, right? Y is equal to e to the 2x minus 4. So we're integrating here then. Well, we times it by pi. So pi times by the integral. Again, we'll come back to limits in a moment. So we've got e to the 2x minus 4 all squared. E to the 2x minus 4 all squared here. Okay. And this is with respect to x here. So in terms of the limits here then, well, the upper limit is nice and straightforward. That's simply ln 4, right? So my upper limit is ln 4, and same again here. Okay, but what about the lower limit here? Well, for the lower limit, that would be when this curve, okay, this curve C here crosses the x-axis, which would be roughly there, right? So in that case then, that will be when y is equal to 0 here. So y is equal to e to the 2x minus 4. So e to the 2x minus 4 is equal to 0. So now add 4 to both sides here. We get e to the 2x equals 4. Now if we take the natural logarithm here of both sides, we get 2x is equal to ln 4. Like so. And then finally here, just divide both sides by 2. So we get x equals ln 4 divided by 2, which is just the same here as ln 2, right? So in that case then, this point here is ln 2. And what that gives us then is the lower limit here to our integral. So ln 2 here, and then same again here. Okay. So now for this bracket, that's squared here, right? You could just do this off the top of your head if you want to. I won't risk it because I know I will make a mistake here if I try and do that under the pressure while I try and make this video. So let's write it down. So I've got e to the 2x minus 4. Then times it by itself again. So e to the 2x minus 4. Like so. So if we expand this out here, e to the 2x times by e to the 2x, we get e to the 4x there. We then have e to the 2x times minus 4, and we repeat that here, right? So in total, then we get minus ae. So minus ae here, the power of 2x. And then finally here we have minus 4 times minus 4. So that gives us positive 16 there. So plus 16, right? Like so. So in that case then, what we have here for the volume V is that V is equal to pi times by the integral then from ln 2 to ln 4 of y squared here, which is just this when we expand it. We have e to the 4x minus ae to the 2x plus 16 there. Okay, and we're integrating here then with respect to x, so dx there. Now to evaluate this integral here then, nice and straightforward, just go term by term here. So in that case then, what do we get here? Well, we get pi times by them. So e to the 4x, when we integrate this here with respect to x, we just divide through by 4. So I get e to the 4x over 4. E to the 4x over 4 there. We then have minus 8e to the 2x. Well, when we integrate this here with respect to x, again, we just divide through. And in this case, we divide through by 2. So a over 2, we get 4. Get minus 4e to the 2x there. Like so. And then finally, this plus 16 would just be plus 16x there. Okay. And don't forget our limits here then from ln 2 to ln 4 here. Okay. So now all we need to do here then is just evaluate the limits. Don't forget we start by substituting in the upper limit here, and then we subtract the lower limit, right? So in that case then, what we get here is pi times by. So what am I going to get here? Well, for a start, let me get rid of the square bracket, right? Because we're evaluating it. So technically incorrect here. We'll do curve bracket. So pi times by. So I get e to the power then of 4 ln 4 over 4. So e to the power of 4 ln 4 over 4. Way too many 4s, right? I'm bound to make a mistake somewhere. We then have minus 4e to the 2x, so minus 4e. In this case, then we get this to the power of 2 ln 4. So 2 ln 4. And then finally here we have 16 ln 4. So 16 ln 4 there. Okay. So these three terms here, this is when we substitute in the upper limit, right? So I'll put this inside a separate bracket here, just so we can separate those, like so. Then we subtract here the lower limit. So hopefully we can just about fit this on underneath here. So in that case then, what do we get? I get e to the power of 4 ln 2 over 4. So e 4 ln 2 over 4. Right, straight away I can see I'm not going to have enough room here. So let me just do it under the line underneath, just so I can separate these, right? So we then have minus here, and I'll do it underneath. So e to the power of 4 ln 2 over 4. All right, this looks a little bit neater here. So e to the power of 4 ln 2 over 4. We then have minus 4e to the power of 2 ln 2. Minus 4e to the power of 2 ln 2. And then finally here we get 16 ln 2. Okay. So this is what we're subtracting here, right? So we subtract this. So what we need to do now then is just deal with all of these powers here, right? And simplify. So all I'd recommend here then is just use a calculator to evaluate all of this. You don't need to do it by hand or do it off the top of your head. Just use the calculator. So in that case, then what I'm going to get here, I'll do it underneath. So we've got pi times by all of this here. So what do we get then? Well, e to the power of 4 ln 4 over 4, that would give me 256 over 4, which is 64. I get 64 there for this term here. We then have minus 4e to the power of 2 ln 4. Again, just use the calculator. If you do this correctly, you should get minus 64 here. And then obviously we've got the 16 ln 4 here. So plus 16 ln 4, like so. I'll come back and simplify it in just a moment. So we then have minus here, and I'll do these terms inside a bracket just so I don't make a mistake with the signs just yet here. So we have e to the power of 4 ln 2 over 4. So what would that give us here? So that would be 16 over 4 there. Obviously because 2 to the power of 4 is 16. So 16 over 4 is 4. I get 4. We then have minus 4e to the power of 2 ln 2. So that would be 4 times 4. So that's 16. So 4 minus 16 there. And then we have plus 16 ln 2 there. So plus 16 ln 2, like so. Well, we're getting there now. We're nearly done here. So we just simplify here. The 64s will just cancel, right? Like so. What we get here then is pi times by 16 ln 4. So pi times by 16 ln 4. So 4 minus 16 would give us minus 12. So minus minus 12 is the same as plus 12, right? And we also have minus 16 ln 2 here. So I've got 16 ln 4 minus 16 ln 2. And then don't forget the plus 12 here. Like so. And then don't forget what we're looking for here is 4 pi, 4 ln 2 plus 3 here. So in that case then, we can factor out a 4 here. We get 4 pi. And then all we also need to do here, not the best English, but you get what I mean, is deal with this single logarithm here, right? So we've got a difference of logs here. So we can write this as a single logarithm. So in that case then, 16 ln 4 minus 16 ln 2. Well, if you factor out the 4, we get 4 ln 4 minus 4 ln 2. Writing this as a single logarithm then, we get 4 ln 2 here. So I get 4 pi, 4 ln 2 here. And then finally, factoring out the 4 here, we get plus 3 there at the very end. Okay, and there we have it. So as required, we've got the volume that we needed to find. Okay, and there you have it. So like you can see, there is often a lot of work involved here for these types of questions that involve volumes of revolution for parametric curves. But, you know, it is a nice little bit of mathematics there. We did get to the end and quite a nice volume there in its exact form. Okay, so there we have it. That gives us the solution to this question here. And that brings us to the end then. I can't even speak anymore. It's been quite a long question. So that brings us to the end then of this video here on volumes of revolution for parametric curves.